All right, so let's understand set. So from here on, everything we do, the sets and then counting techniques, all that will be preparation for probability. So if this material, you have to learn this material very well to be able to understand the probability and statistics. So the next two topics, sets and then counting techniques, these two topics are basically preparation for probability. So if you do poorly here, you'll have trouble understanding probability. But fortunately, this topic is fairly easy. Set theory is very easy. So you should be able to handle this one well, but the counting technique is not that easy. Anyway, let's begin the set theory. A set is a collection of objects. So the objects can be anything. It can be numbers, letters, people, doesn't matter. Any objects of interest. You collect them, collect a bunch of them, then it's called a set. Now to write down the set, to describe the set, there are two ways. One of them is called listing method or roster method, in which in this method you basically write curly brackets and then list all the elements inside. List all the elements inside the curly brackets. That's what we call listing method or roster method. I'm giving you both names because books use both. Some books use the roster method, some books use listing method. So you should understand that they're both the same. We usually use uppercase letters to identify sets, to name the sets. So I'm saying A equal to, and that means I'm naming this set as A. All right, so here's an example. The problem says set K consists 579. So write down the set. This is how you write it. Now, if you must write the curly brackets. If you don't put the curly brackets, it's not set, it's just a list. So to identify something as set, you need the curly brackets. The elements are listed inside the curly bracket. So that's why it's called the listing method. The other one is called set builder notation. Now, we cannot always list all the elements in our set. And that's when we use this set builder notation. We'll see examples in a minute. In the set builder notation, you write the name of the set, and then in the curly bracket, you always write X. Basically, you're representing all your items in the set by the symbol X, and then you describe the conditions on X. What are the properties of X? You describe that inside. And when we read it, we read the curly bracket as set. So basically set of all X such that this line will be read as such that. So set of all X such that X is this, whatever the rule is. So here's an example. The set of all positive integers. Now all the positive integers, that's infinitely many. So we cannot write them down. That's when we use the set builder notation. The set of all positive numbers cannot be written by listing method, so we write it this way. C equal to. C is just a name. You can make up any name, A or B or C, doesn't matter. Set of all X such that X is greater than 0, X is integer. So all the number is supposed to be positive integer. So there are two rules, positive and then integer. So you write down those rules. There may be more than two rules. There may be sometimes one rule, doesn't matter. You can list all the rules inside. That describes the entire set. So this set, we cannot convert it to a list. We cannot write this set as a list. It can only be written this way using the set builder notation. All right, so let's see some exercise problems. The three sets are given. four sets, A equal to 357, B equal to 735, 4862, and 28. And N is described by this because, well, they decide to describe this set using the set builder notation. And so it's a single digit number. X, it's set of all X such that X is a single digit number. E, set of all X such that it's even single digit number, odd single digit number. So that those are the sets F. And now the problem says, exercise 1 says, rewrite these sets N, E, and F by listing the elements. So this, if you look at the set N, you can actually rewrite that set by listing the elements. So let's list them. I have to use the curly bracket and then list all the items. What are the numbers in that set? Single digit numbers are finitely many. They're not very, it's not a long list. So we can write them. What are they?
1 through.
Say again?
It's 1 through 9.
1 through 9 and 0 too. 0 through 9. So 0, comma, 1, comma, 2, comma, 3. Can you use dot, dot, dot? Yes. So feel free to do that. When the pattern is clear, you can use dot, dot, dot. Okay, so E says even single digit number. Can somebody tell me what they are? You may have to unmute yourself to answer the question.
2, 4, 6.
2, 4, 6, 8, right? And that's it. Because it has to be single digit number, so even single digit number will be just that. Okay. Now remember, you have to use curly bracket. Any other bracket is not acceptable. I'm telling you because when you enter the answer in your waiver sign, you must enter with the curly bracket. They usually have the curly bracket already, and you have to enter the items inside. All right. What's the answer for F? Anybody?
1, 3, 5, 7, 9.
Wow. Okay. Very good. So now let's move on. Exercise 2 says rewrite these sets described in words by using set builder notation. They are described, they're simply described in words, but we had to use set builder notation. So I begin by saying set of all X. Remember, set builder notation means set of all X, such that, what do I write inside?
Greater than?
All the numbers less than 10, that's the statement, right?
You write the less than sign. You put the line after, I think, and then you write the less than sign and then put 10.
Did you say 9? I don't have to write 9 anywhere. See, this is all the numbers less than 10, not just the whole numbers. So we cannot list them clearly, right? We don't even know the smallest number less than 10. We can't even write that down. The smallest number in the world, can you tell me what that is? We can't tell. So that's why we have to use this notation. And so inside the curly bracket, after the vertical line represents such that, what condition do I write?
X smaller than 10.
X smaller than 10, right? That's all. And so that's our answer. Set of all X such that X less than 10. Because all the numbers less than 10 means X has to be less than 10. That's the only condition. All right, so let's go to the second question. All positive integers less than 10. So always you have to write set of all X and then such that
X greater than 10.
X, all positive integers,
10 greater than X.
X greater than 0, but smaller than 10.
exactly. So X has to be greater than 0 and less than 10 at the same time. So that can be written in this way. Let me write one way first. 0 less than X less than 10. See, this means X is greater than 0 at the same time less than 10. X is between 0 and 10. Basically, that's what it says. And that's exactly what the statement says. Now, do you have to write it this way? Is there other ways? There are other ways. If you write it in any way, that'll be acceptable as long as it represents the same thing. So you can say X less than 0 as one inequality, and then X, X greater than 0. X greater than 0 as one inequality, comma, X less than 10 as a separate inequality. It's not wrong. That will be also correct. Okay, so either one of those will be right. And now this one says all the numbers between 10 and 15. That's kind of similar to that. So I'm going to go ahead and write that for you. Set of all X. Am I getting bored? Set of all X. All right, doesn't matter, such that X is, so 10 is between 10 and 15 means 10 less than X less than 15. Now, when do you use less than or equal? Only if it says all the numbers between 10 and 15 inclusive. The inclusive word, if you throw that in, it means the endpoints are included. That's when you use less than or equal to. Okay, so that settles that. Now let's understand some symbols. In set theory, we use some symbols to mean some words. So if you need to say something belongs to a set, the word belongs to can be written by writing this symbol. So it's, let me write on the board. It's like the symbol of some, select the pencil. Okay. So it's like the C with the line in the middle. That's how you write it. So it's called belongs to. Actually, it's a little bit more curved C. This symbol means belongs to. So if I want to say a number belongs to a set, then I can use this. Whenever I want to say something doesn't belong to a set, we cross this out. The same symbol crossed out means does not belong to. Okay, so if set K consists of, actually example 1, if you look at example 1, this set K consists of 5, 7, 9. I'm going to copy and paste that here so that you can see. Set K consists of 5, 7, and 9. So 7 belongs to K. So I can say this is true. Some questions in your homework may say true or false. By the way, if it is true or false, then there is only one possible answer. So for that kind of question, you will not get more than one chance to do it. Clearly, you know, after you try the first answer, you know. If it is wrong, you know what the right answer is because there are only two answers. So you only get only get one chance. Normally you get 3 chances, but for a problem that has only 2 answers, you only have 1 chance. All right, 7 belongs to K is true, and 11 does not belong to K. Is that true or false?
It doesn't belong to K.
So this statement, is that true or false?
True.
It's true, because 11 doesn't belong to K is true. Okay, now The same set for K. This is a set we are working with. Is this true or false?
False.
Oh, wait, hold on.
True.
No, we are not dealing with this set. It's referring to A, set A, B, these sets. So now we are referring to these sets. So let me copy those and place them here. So we are dealing with these sets here. So A is right here. So 5 belongs to A. Is that true? Anybody?
Yeah.
Yes. 5 belongs to F. F is odd single digit number.
Yes.
Yes. 0 does not belong to A.
It's true.
True.
True. 7 does not belong to A.
False.
False.
False. The set 3, 5 belongs to A. You would tend to say true, but it's not, because 3 belongs to A is true, 5 belongs to A is true, but 3, 5 with the curly bracket is a set. A set cannot belong to the set A. Okay. The notation matters. So if I simply say 3 belongs to A, that's true. 5 belongs to A is true. If I don't have the curly bracket, you can argue that it's true, but the curly bracket makes it a set. The set cannot belong to a set. So that statement is false. Okay, moving on. Let's understand.
I have a question.
Sure.
So for each of these problems, will they have their own set of statements, or are these statements that we have to remember for all of these type of problems?
No. It's this problem, this definition, these definitions were given. You don't need to memorize that. For another, in any other problem, they'll have their own definition of the sets.
Okay.
All right. Yeah. No memorizing is needed anywhere here. Of course, you need to remember the basic facts, these symbols, what they mean, and everything. Subsets. If all the elements of the set A belong to the set B, everything in A is also in B, then we say A is subset of B. Everything in A must be in B. If there is one element that's not in B, then it's not subset. So if A is subset of B, then we write this. So it's basically, the notation here is like U written sideways. And we put equal, this line underneath basically says it can be equal. It's just like less than or equal. Less than means less than. If you allow a line underneath it, it's now less than or equal. That means equality is allowed there. So this line here means it can be equal. So even if A and B are equal, we can still say A is subset of B. If everything in A is in B, then we can say A is subset of B. So that's how we write A subset of B. The subset has to be on this curly side of the symbol. This is a subset of that. The equality is allowed. Equality is possible. That's when that's what the line underneath means. Okay, so here's an example. The A, so whenever we want to say A is not subset of B, it'll be the same symbol crossed out. There will be no line underneath. The same symbol, curly symbol, will be crossed out to mean not subset. Okay, so let's see the examples. A is 246, B has these numbers, C has 249. The question is, are these statements true? A subset of B, that's what this says. Is that true?
Yes.
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 Everything in A is also in B. So that's when A is subset of B. Second statement says A is not subset of C. Is that true?
No.
Yes, it is.
It is true, because A has the number 6 that does not in C. So all the elements,
So it would need to have all those three numbers to be the same?
Yes, all
Okay.
these numbers must be there in C, only then it's subset. The 6 is missing, so it's not subset. So therefore, A is not subset of C is true. All right, so now we have an exercise. The A, B, C, D, and N, E, F are these right here at the top. I copied and pasted. These are our sets. For those sets, is A subset of E true?
No.
No, false. Correct. If anybody is not following me, please ask the question. E subset of F?
No.
No, false. F subset of E?
False.
False. E subset of N?
True.
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 Because N has all the single digit numbers, E has even single digit numbers. So all the even single digit numbers are also there in all the single digit numbers. So we actually wrote down the sets up here. So we can even copy and paste that. Then you'll be able to see. The N, E, and F are these. You can see that everything in E is also here. 2, 4, 8, 2, 4, 6, 8, all of them are there in N. So therefore, E subset of N is true. And B not subset of C.
True.
B not subset of C is true, yes. The elements in B are not in C. Okay, A is not subset of N. Is that true?
False.
A has 3, 5, 7, and N has 0 through 9. So 3, 5, 7 are there, right? In N. Because N has all the single digit numbers from 0 to 9. So therefore 3, 5, and 7 are in N. So A subset of A is actually subset of N. Agree with that? Oh, by the way, Petrusaj, are there 2 students with that last name? Petrusaj.
Yeah, that's me and my sister.
Ah, that's your sister. Okay. I
Yep.
was kind of wondering, you know, that there are 2 students with the same last name. I was kind of I wanted to confirm that. Okay. All right. So A subset of N, A is actually subset of N. So A not subset of N is false. So this is false. Next statement says A is not subset of B. So let's go back to the sets. Here's the A, B, C. A subset of A and B are compared. 3, 5, 7. B has 7, 3, 5. So A not subset of B. Is that true or false?
It's false.
False. Everything in A is in B. 3, 5, 7 are all there. Not in the order, but order doesn't matter. In sets, order doesn't matter. So therefore, A and A, all the elements of A are there in B. So therefore, A is actually subset of B. So this statement is false. This says 3, 5, 3, 5 as a set is subset of A. A is this. So is that true or false?
That's true.
It's true. 3, 5 with a curly bracket around it is a set. And is that subset of this set A? Yes. All those elements 3 and 5 are here in A. So that statement is true. Okay, so let's move on to equality of sets. 2 sets are equal if and only if 2 sets A and B are equal if and only if A is subset of B and B is subset of A. In other words, everything in A must be in B, everything in B must be in A. Only then they are equal. So let's go up here. I just saw one set. How about these two sets? Are these two sets equal?
Yes.
Yes.
Yes. Everything in A is in B, everything in B is in A. See, remember, order doesn't matter. So these two sets are equal. So that's when they're equal. Everything matches. Only the order is different. All right. So here's some example. Again, it's based on these sets. So I'm going to copy and paste them here. Exercise 5. Size based on the sets A, B, C, D, N, E, F, which I'm pasting right here. For these, A equal to B, I just asked that question. It is true, right? A equal to B is true. A equal to F,
True.
is that true? Okay. F has odd single digit number, which would be 1, 3, 5, 7, 9. So A subset of that is true, but A subset of F it will be true, but A is not equal to F, right? To be equal, everything in F must be in A as well, which we don't have. So therefore, this is false. A subset of F would be correct, but A equal to F is false. C not equal to F. Is that true or false?
True.
True. C is not equal to F is true. C not equal to E.
False.
False.
E has even single digit numbers, which will be 2, 4, 6, 8. And C has the same thing. So they are equal. So therefore that statement is false. If anybody is not following me, feel free to ask the question. All right, now empty set. An empty set is a set that contains nothing. We will run into such sets, a set that contains nothing. And we have two notations for it. Curly bracket with nothing written inside will be one notation. More commonly used notation is this symbol. You read it as phi. It's basically like similar to having O, capital O crossed out. It's a Greek letter called phi, and most of the set theory and some other mathematical theories were developed by Greek mathematicians, and that's why we still use Greek letters to represent things. So this symbol itself means set. So don't put curly bracket around it whenever you need to write empty set. It already is a set. So phi is the empty set. So whenever you need to say this set is empty, you can say, whenever you want to say A is empty, set A is empty, you can say A equal to phi. That means A is empty. So going on to exercise 6, the set A has 3, 5, 6. B has all the single digit numbers. So B basically has one single digit number. So that's same as this, 0 through 9. That's what B is. A subset of B. Is that true or false?
True.
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 That's right. That's true. Phi subset of A.
True.
True. Yes. Okay. One student answered it correctly. Why phi subset of A? Phi is a set that has nothing. So everything in phi is in A because phi has nothing. That's how the logic goes. Everything in phi is in A because phi has nothing. So is phi subset of B?
False.
Yes. So basically, phi is a subset of any set.
Wait, can you explain to me what's the difference between phi being the subset of A and then not being of B?
I didn't say not subset of B. I said it is subset of B.
Oh, I thought you didn't. I'm sorry.
Phi is subset of every set we deal with. Okay, because it has nothing in it. All right, let's move on to a universal set. The universal set is the larger set that from which all the elements we are working with are drawn. So in other words, you have to look at the working sets, the sets that we are dealing with, and then come up with an explanation as to what are we dealing with, what objects we are dealing with, that, and put all of them together into a larger set. That's what the universal set is. So here, this example will make it clear. I'm doing a problem in which the set A has 3, 9, 11, 15. Set B has these numbers. Then what would be the universal set for my problem? Set of all positive integers. So here is how I described it. Because I'm dealing with the numbers and they are positive, as you can see. I'm not dealing with negative numbers. So set of all positive number will be correct, or even narrower universal set will be set of all positive integers, because these are whole numbers, right? We don't have fractional numbers. So we can narrow it down to a smaller universal set, which is set of all positive integers. So you have to make sure all your sets, all the sets you're dealing with are subsets of the universal set that you chose. So whatever the universal set you identify, your sets must be a subset of that, all your sets. So that's when your universal set is correct. So instead of saying my universal set is set of all x such that x is integer, if I just say set of all x such that x is positive, then that would be all positive numbers, not integers, not necessarily integers. So that would be a larger set than this. Is that a correct universal set? Yes, that is also correct. The universal set can be any set for which all your sets are subsets. But in problems that have to deal with universal set, the problem will tell you what the universal set is, because universal set is not unique. It can be anything. So therefore, they will tell you what it is. So you don't have to guess yourself. But I'm asking two questions here in exercise 7. If my working sets are these, what would you identify your universal set as? Set of all? Anybody? You have to unmute yourself.
Would it be set of all integers?
And look at my sets. Do I have integers here? Are you looking at set A in exercise 7?
No, there's no integers.
Yeah, so
X is letters.
letters. Set of all alphabets. That will be a universal set. Okay, look at these sets. What would be the universal set for this?
X is less than 0.
All integers less than 0, right? All negative integers, that's right. If you say all numbers, that's also correct, but you want to narrow it down. Whenever problem asks you for the universal set, try to identify the smallest universal set. But you won't be asked that question.
I have a question.
Sure. Go ahead.
When we make it the universal set, do we have to like when you like how you have x is integer and then you have x is greater than 0? Do we have to write it like that? Put the words first and then the symbols?
Yes, you have to use set builder notation like this. I'm writing the answer for B. I'm writing set of all X such that X less than 0, right? That's one rule, and X is integer. So that's how I describe that universal set. Clearly, it's infinitely long.
How will you do the one? How will
But-
you do the one before that one? The one with the
okay, you can write it as set of all X such that X is, I'm sorry, such that has to be vertical. X is an alphabet. Okay, that's how you describe that. So universal sets are usually infinitely long, so you have to use set builder notation. All right, so if A and B are two working sets and U is the universal set, is this correct statement? A and B are the sets we are working with, and we know
It's true.
yes, U is the universal set, then A has to be subset of B, a subset of U. B also has to be subset of U. A subset of B may not be true. That depends on what they are. We don't know what they are, but no matter what they are, this is always true. All our working sets must be subsets of the universal set. So that must be always true. Okay, now we are ready for the Venn diagram. The Venn diagram is a tool that makes the set theory problems easier to solve. And the mathematician who came up with this idea was Venn. Venn is his name. So his name is given to this idea. It's a powerful tool. It's very useful to solve set theory problems. Now we are preparing ourselves right now to do set theory problems, real life application problems that can be solved by this theory, set theory. And to be able to do that, we're going to have to use this tool. And so basically, you're going to use some diagrams to represent sets. And in this method of Venn diagram, you would identify the universal set by a rectangle. So let me go to the board. If I want to show the universal set in the Venn diagram, I would use a rectangular box, which means all the points in here. The universal set usually has infinitely many pieces of data. So all these points here represent the items in the universal set. That's what it means. So the dots inside the box represent all the items, all the things in the set. So if you any set that we are going to work with will be subset of universal set. So we use a circle inside this rectangle. This circle represents a set I'm dealing with. Every working set is going to be a circle inside the rectangle because they're all going to be subset of the rectangle. So this, if I put this circle and say this is my set A, and I put the name A outside like that, then all the dots inside here are the points of the set A, or the elements of the set A, and they're all inside the rectangle as well, the universal set. By the way, universal set is identified by the letter U. So all these points are inside the rectangle as well. So this properly indicates that A is a subset of U. Everything in A is in U. Now, another set I'm dealing with would be a circle inside the U. So this set has these points, and this set B is not sharing any element with A. So if two sets are sharing some elements, then I will show that as A being this and B being this. Now they are sharing some elements. Some elements are common to both. And so if that's true, then that's how I show that. All right, with that understanding, so I have that picture, example 6. This picture shows that A and B are two working sets that share some elements. Let's do the exercise 9. A and B are two working sets. U is the universal set. Draw the Venn diagram to represent each indicated facts. A is actually subset of B. How would you draw your picture to show that on the Venn diagram? Just tell me in words. How would you draw that? A is subset of B. What does that mean? Everything in A must be in B, right?
So you would draw them together, like not together, but like, you know, crossing perhaps.
No, circle
like
A
the
will be
first graph.
inside circle B.
Circle for A would be?
Inside of circle B.
Inside the circle B. That's how it would be. So B will be a larger circle. A has to be smaller circle inside. Only now, every point in A is also in B, isn't it? Right? So the points represent the elements. So now every point in A is also in B. So this shows that A is subset of B. And if A is subset of B, that's how you draw that. Now this problem, part B of exercise 9 says the two sets don't share any element. How would you show that in a picture, in a Venn diagram? The two sets A and B are not really sharing any element. There's nothing common to them.
There'll be two separate circles.
Separate circles, that's right. A will be like this, B will be like this, and not sharing anything. That's how you show that. Very good. All right. Glad to see that you were able to answer that. The set operations next. Set operations means operations with sets, just like operations with numbers would be addition, subtraction, multiplication, just like that. We can carry out operations with sets, and that's what we need to understand now. If A and B are two sets, then A intersection B, that's what we read. We read this as A intersection B. This symbol, which is basically upside down U, is the symbol for intersection. And what is the meaning of intersection? Elements that are common to both sets will be in the intersection. So A intersection B will be another set, which contains all the elements that are common to A and B. That's one set operation. We're going to do example in a minute. Now let's understand union. We write it as A, U, B. U is the first word of union, and that's the symbol for union. So I'm doing an operation with these two sets, and what will it give me? It'll give me a new set, which will contain all the elements of A and B combined. So union means combining, putting them together. That'll be a larger set. A intersection means finding the common elements between the two. So both of them, both operations will produce a new set. The new set will have, if it is intersection, the new set will have all the elements that are common to A and B. If it is union, the new set will have all the elements that are in A and B combined. So let's do an example. The sets A has 2, 4, 6, 8, B has these, and C has 1, 3, 5. Then A intersection B would be elements that are common to A and B. Look at A and B. What are the common elements? 4 is there in A and in B. 8 is also there in A and in B. And that's it. Nothing else. You have to identify all the elements that are common. put them together as a set. That set is your answer for A intersection B. A union B means everything in A and everything in B should be collected together, but you don't write same elements twice. So for example, 4 is here in A and in B. You write the 4 only once in the union. So union has 2, 4, 5, 6, 8, 9, because we had to combine all these elements in A and the elements in B into one set, and that's what this is, union, right here. Okay, B intersection C. If you look at B and C, the elements that are common would be only 5. So if you have only one element, you still have to write it as a set with a curly bracket, because the intersection is supposed to be set, not a number. So remember to write the curly bracket when you're writing a set. Okay, what is, oops. I meant to open the other one. All right, let's look at this exercise 10. A, B, C are these sets right here. Then what is A intersection C? A intersection C. C has these elements. A has 2, 4, 6, 8. So what will be your answer for A intersection C?
There's nothing in common, so it's empty.
So what you write as answer, you write A intersection C
Equals to phi.
equal to phi, that's right. Because A intersection C is empty. So empty means you write okay, so you write the phi next to it. This phi is slightly different looking, but doesn't matter. So that's how you answer that question. You can use the words empty set, but you're expected to use the phi to answer that question. So let's do the exercise 11 and 12. Exercise 11 has these A, B, C. So what is A intersection B? So go ahead and do that on your piece of paper and then tell me your answers. Or if you can tell me right away, go ahead.
D and F.
Part A first, A intersection B. What's that again? Or you have an answer. Okay, go ahead.
D and F.
D and F are right. Yes, D and F is correct. So it's a set containing D and F. Curly set, curly bracket, D, comma, F will be correct. B intersection C.
G.
It's just G. So can I write like that?
No, you have to do the parentheses.
Right, the curly brackets have to go there. A intersection C.
Is it phi?
Phi is correct. Yes.
Okay.
P is the answer for that. A intersection B intersection D. Now remember, this means what is common to all three sets, A, B, and D. Okay.
It's F.
F.
F. Right. Okay. So these operations can be multiplied. You know, I can have 4 intersections. That means common to all of them. All right, disjoint sets. 2 sets are said to be disjoint if the intersection is empty. If the intersection is empty, then there are nothing common, like this one in the picture here. These two sets, A and B here, are disjoint because they have nothing in common. They don't share any element. Okay, so we don't need to do that exercise, but let's go ahead and do these. Exercise 13. A, B, C, D are given here, and it says find A union B. Okay, can somebody tell me what to write in A union B?
Curly bracket D
It's union.
and comma F. Oh, C then? I'm sorry.
Yeah, you're doing intersection, I guess. It's union, so?
It'll be C, comma D, comma E, F, G, H.
Yeah, E, comma, H, all of them. Okay, I can leave those. Let's go to the D part, A union B union C.
A.
Yeah, even though the order doesn't matter, I recommend writing them in order. That way you won't miss anything. So I'm going to try to write them in order. Yeah, go ahead.
Okay.
A, B2, right?
C.
C, D, E, F. Anything else?
G.
G, H, isn't it? G and H are there in B. We are combining A, B, and C. So that's the answer for that. Okay, part E says A union B intersection C. See, there's a parentheses that tells you which operation has to be done first. A union B has to be done first. We did that here. So this is our A union B. So now, so you had to do that first, A union B. Then find intersection of that with C. So what is common to this set and C? That's what we need.
G.
G only the G. So you write G as your answer. As you can see, there are multiple operations, a union and intersection. So when that happens, you have to do them in the right order, otherwise it'll be wrong. This one, A intersection B union C, means I had to find the intersection first, A intersection B. A intersection B has
D.
D
And F.
and F, D and F. So A intersection B has D and F, and I need to combine that with C. So D, comma, F, comma, everything in C has to go there. That'll be A, B, and G. So A, B, and G. So you don't really have to write them in order, but I recommend writing them in order so that you won't miss anything. But this is correct answer for that, D, F, A, B, G. All right, so let's now see how to show things on Venn diagram. So A intersection, this problem says, shade the region that represents each set. So I need to shade the region that represents A intersection B on a Venn diagram. So what would you shade in this case? I'm writing on the
Space
board.
in the middle.
Right, okay, you said it right. The part of the part in the middle of the two sets. In other words, I'm drawing on the board. This is what you will do as your answer. You show the two sets A and B, and the problem says shade the region that represents A intersection B. A intersection B will be these dots, isn't it? Everything that's common to A and B. So you shade the region by using this kind of shading, and that's your answer. That shading is the answer. Okay, can somebody tell me what to shade for part B?
Both circles.
What's that again?
The
Both
two
circles.
circles,
Both.
the A and B circles.
Yes, both circles should be shaded because A union B means everything in A and B combined. So all the dots in A and all the dots in B should be combined. So that would be this. This is your answer for that question. Part C says A union B intersection C. Okay, so that means I have to find B intersection C first, and then I had to combine it with A, right? So I'm going to go step by step and show you how to do that. B intersect, so there are 3 sets involved now. So I will find, let them all intersect unless problem says otherwise. This is A, B, and C. So B intersection A, I'm sorry, A union C, which one are we doing? We're doing part C, which is A union B intersection C. B intersection C, I'm going to mark that first. That's this, right? What is common to B and C. Now to this, I need to combine the entire A. That's the meaning of A union, right? I need to combine entire A to this. Entire A, when I combine, all of the A will be shaded along with the shaded part I have already. So this combined with this. So now I have combined the answer. I have shaded the entire answer correctly. You're going to be doing this in your homework. So make sure you understand, otherwise ask the question. So this one, the next one is probably the most difficult out of these. A union C intersection B. Okay, so to do that, I'm going to do a work picture. This is my work picture. I'm not showing my answer here. This is A, B, and C. Okay. According to problem, I need to find A union C. A union C is these 2 circles together, and find what is common to that and B. So I'm going to use shading here, but this shading is not answer, this is just work. I'm shading A union C just to show that, just to highlight that. A and C combined, right? That's A union C right there. All of that is A union C. Now you ask the question, what is common to this shaded set and B? Isn't that the question here? A union C intersection B, right? So what is your answer then? What part, basically the question is, what part of the shaded region is also in B?
The center?
Yes. So I'm going to shade that in red. This is the part, this is the shaded part that's also in B. So this will be our answer. A union B, A union C intersection B. The answer is exactly that. So now I'm going to show the answer.
Question?
Yeah.
For the homework assignment, when we would get a question like this, would we be able to change the colors too, or would they like submit our answer as soon as we do the shading?
No, on WebAssign, it'll be multiple choice question. Because
Okay.
they can't let you draw anything on WebAssign. So it'll be multiple choice. So here's my answer to the question. This, what I have done is work. You can do that on a piece of paper separately, but when you present the answer, you have to show only the answer shaded, okay? So here is the answer. This is our answer to that question, okay? With this being A, B, and C. So WebAssign questions on the Venn diagram will be mostly multiple choice. You have to choose the correct answer. All right. So stopping here, we are now out of time.